In the last video, we introduced the Solow model and we did some calculations and found that eventually the Solow model reaches a steady state in terms of capital per effective worker. And we calculated what that steady state is. Now I want to think about transition dynamics in the Solow model. So let me write out our equation. And I'm going to drop the time subscripts just for sake of ease. And I'm actually also going to just call capital per effective worker K rather than K tilde, just to save on notation. So we found out that capital per effective worker evolves according to the following equation. Now this is called a Bernoulli differential equation. And in general, for any Bernoulli differential equation, we can solve it completely. So we can derive a function K of t, of time, and find out what the level of capital stock is in an economy at any point in time. And in general, for Bernoulli equations, and in order to do that, you use a change of variable. I'm going to call a variable x. I'm going to define it as k to the power of 1 minus this power over here, which is alpha. So as I say, this is a general tool to solve Bernoulli differential equations. But in the case of the Solow model, this actually has an economic interpretation because, of course, this is the capital output ratio. And we're going to see that the Solow model, although it is defined by an equation that is of this form in terms of k, in terms of x, it's actually a linear equation. And we can solve that very easily. We do this as follows. So let's find the derivative of x with respect to time. So we use the chain rule here. There's, of course, 1 minus alpha times k to the minus alpha times k dot. But we know what k dot is. We're given that initially. It's as follows. Sk to the alpha minus this term. And now we can cancel a lot of stuff here. So we get 1 minus alpha times s, but the k to the minus alpha and the k to the alpha just cancel. Minus this term here. And now we get k to the 1 minus alpha, but this is, of course, how we defined x. So now we've derived a linear differential equation in terms of x, which is the capital output ratio. And just to make things a little tidier here, I'm also going to define this as gamma, just so I don't have to keep writing out that whole thing. So we get that x dot is equal to, I'll actually rewrite this as plus gamma x equals 1 minus alpha s. Now, to solve a linear differential equation of this form, which is a non-homogeneous differential equation because we have this constant term on the right-hand side, we can introduce an integrating factor. And our integrating factor here is going to be e to the power of gamma t, where gamma is our coefficient on the x here. And I'm going to multiply both sides of this differential equation by our integrating factor. And now I'm going to integrate both sides with respect to time. And the reason we introduce this integrating factor is because the integral of this term here is just x times e to the gamma t. So if you differentiate this with respect to time using the product rule, you'll see this is equal to x dot times e to the gamma t plus gamma times x e to the gamma t. So that's why we introduced that factor. And on the right-hand side, this integral, we can integrate it with respect to t. So we have to divide by gamma. I get e to the gamma t. And we need a coefficient of integration. I'll just call it c. Now we can rearrange this in terms of x. So we get x, and I'll write it as a function of t now, just for the sake of it. And if we divide both sides by gamma to the minus e to the minus gamma t, we're just going to get a constant term here, c times e to the minus gamma t. And now we can figure out what C is. So when t is 0, write it over here, when t equals 0, x of 0 is just equal to 1 minus alpha times s over gamma plus c. And remember, x0 is just k0 to the power of 1 minus alpha. So the value of c is going to be given by our initial level of the capital stock. If k0 is given by some amount, I'll call it k0, then c has to be given by the following. Okay, and now we can plug this value of c into our equation for x. And I'll write it in terms of k now. So we get kt to the power of 1 minus alpha is equal to this constant plus our initial condition, and all times this e to the minus gamma t. And if we want, we can rearrange this a little bit to collect the 1 minus alpha times s over gamma term, but we don't need to do that. In particular, this is nice because we see as t goes to infinity, this term is going to go to 0, and our capital output ratio, which is on the left-hand side, is going to approach this constant. And the initial condition is not going to have any effect. So let me also just rewrite this, but plugging in the value of gamma. Remember, gamma was this constant up here. So we have a 1 minus alpha and a 1 minus alpha, so I can cancel that. We get s over delta plus g plus n. And the same thing here. Okay, now if we want, we can also rewrite this in terms of the capital stock. We can just raise everything to the power of 1 over 1 minus alpha. And so you see that as t goes to infinity, this term goes to 0, like I said, and our capital stock per effective worker approaches this. So as t goes to infinity, capital stock per effective worker approaches this constant value, which we found in the last video was our steady state value of capital stock per effective worker. So as we expected, capital stock in the long run approaches a steady state value given by this expression here. But this equation is really nice because it allows us to figure out what capital stock per effective worker is going to be at any point in time from any initial condition. Thanks very much. I'll see you in the next video.